Welcome students. Today we are going to discuss about optimization problems. So what is an optimization problem? So many important applied problems involve finding the best way to accomplish certain tasks and are often referred to optimization problems. Say for example, you are in a field and you want to move from point A to point B. You want to say what is the shortest path I can take, right? Isn't it? So that is one kind of optimization problem. Yeah. Say, for example, finding the minimum cost of doing a task. That is also an optimization problem. Finding the maximum power that can be generated by a device. Yeah, that is an optimization problem. Yeah. So, for example, a plane. What is the best way from going from A to B using a plane, but with a minimum amount of fuel? That is also an optimization problem. Okay. So most of these problems can be modeled using function, and then the extreme values can be found using techniques of calculus. So here is where our knowledge of calculus comes handy. So for example, you'll have optimize a function f of x given the constraint that your x is between a and b. Now we have seen similar problems, particularly the case where f was continuous on a closed interval AB using closed interval method for absolute maximum and minimum. Okay. So note that in this case, we are only interested in what the function between the values of A and B. What happens outside doesn't really matter. And we want to know the global extrema of the function. What is the absolute maximum or absolute minimum, depending on whether you want to maximize or you want to minimize the function. So these are the guidelines for optimization. So generally you'll be given a problem, a word problem, and you will have to identify out of it what do you want to optimize and what the constraints are on the optimization. You should draw the diagram if appropriate and label it. Decide what the units are and what units are going to be measured in. Then you have to write down the formula of the function you want to optimize. Okay? Call it whatever, f of x, g of x. Now, sometimes you may have, say, suppose, let's see the following. So suppose I have x plus y equals to 50 and I have xy. So maximize xy given that x plus y is 50. Yeah. So now this is an optimization problem, right? Here, of course, you're not drawing any label. You want to maximize xy. Now, in this case, you're given two variables really, but the constraint, which is x plus y equals to 50, helps you to make it the function of one variable. Why is that? Because this is same as saying y equals to 50 minus x. And when you put it back here, you get x times 50 minus x. So the idea is in the end, you should be basically getting a function of one variable so that you can optimize that. Now, again, you have to identify the domain of the function, whether it's a closed interval. Typically, it will be either a closed interval AB or an open interval AB. So if you have a closed interval, remember how you found out the absolute maximum and absolute minimum. You found out the critical points, you found out the values at the endpoint, and then you compared. However, if the interval is open, you will have to basically say, suppose you have open interval AB, then you'll have to find out limit at x goes to a plus. So if you have here, you have to find limit as x goes to a plus, or you have to do the curve sketching if the interval is open and to determine the absolute extremum. And at the end of it, whenever you find the absolute extremum, you have to convert your problem back into the expression, including the units, right? So there are a few more discussion about it. So So step 6 here is very important. It's crucial to determine the absolute extrema. So there are several methods available to us. So we are digressing on step 6. So suppose f is continuous and its domain is closed. So this we have already seen. Find the guidelines use the guidelines for finding absolute extrema. Now, case 2, suppose if f is continuous and the domain is open, then use the first derivative test to classify the critical point, and then do the endpoint analysis, which is given below here. So what is the endpoint analysis? If the domain is open or unbounded like this, calculate limit of x goes to a plus f of x and limit of x goes to infinity of f of x, and then compare the values at the critical point and the values obtained here and determine the absolute maximum and absolute minimum if they exist. Right? So now, if it is open interval AB, it is not A infinity, then you will need to go both at A and B. So you will approach to A from here. So limit as x goes to A plus f of x, limit as x goes to B. You're approaching B from this side. So x goes to B minus f of x, and compare these values with the critical point and see the absolute maximum and absolute minimum. Okay. So note that there can be many combinations of open and closed domain, and we'll have to follow the similar endpoint analysis for them. Second, if f is discontinuous, suppose f is discontinuous and it has open intervals like that, it's only continuous on this pieces, then you'll have to do each of them separately and combine them. Right. So let's work it out with an example. So here, find the maximum value of h of x equals to e to the power 2x minus x squared. So there are two ways to do it. One is either you take h prime, find the critical point, h double prime, and see if it is absolute maximum or absolute minimum. So you'll find local maximum or local minimum, and then you'll argue a bit further why that becomes absolute maximum or absolute minimum. All right, so let's look at this method, which is quite interesting. So observe that g of x equals to e to the x is always increasing. So I can write my h of x as g of f of x, right? So what do I get? I get my h prime x equals to g prime f of x multiplied by f prime of x. This is the consequence of the chain rule. What is my g and f? G is e to the power x, and f is 2 to the x minus x squared. Yeah. So now note that g prime can never be 0, right? Why? Because it's an exponential function. Exponentials are never 0. So only way you can get 0 for h prime x is when f prime is 0, right? So hence the location of maximum is also the location of maximum for f of x equals to 2 minus x squared. That's very clever. Now, because instead of looking at e to the power 2 minus x squared, now you're looking at f of x equals to 2 minus x squared. So now let's apply the guidelines for optimization. So here are the guidelines for optimization. So identify, draw diagram. This is not necessary. Decide what are the variables. This is not necessary. The formula is already given to you. There is no constraint, and you have what? Find the critical point. So let's find the critical point of this guy. So for function, finding critical point is take f prime x and equate it to 0. In that case, you will get f prime x is 2 minus 2x. So this equals to 0 gives me 2 equals to 2x, which gives me x equals to 1. Similarly, f prime x does not exist. This should also give you some critical points, but in this case, the derivative always exists. So there is no such x coming. Now look at the second derivative test. So we are going to determine whether it's local, or other word for local is relative extrema. So look at f double prime x, which is minus 2 less than 0. So this is always concave down. So always concave down here. And this is the maximum because it's an inverted parabola. F has absolute maximum at x equals to 1. So therefore, the maximum value of h is g of 1, because after all, you're finding the function here. So this is going to be g of, so this is going to be h of 1, which is e to the power 2 minus 1, which is going to be e. So that is the maximum value of your function. Now note that you could have done it directly without going through this. Find h prime x, equate it to 0. So equating this to 0 is same as finding this will never be 0. So therefore you get x equals to 1, and then you can proceed the same way. Okay. So let's look at another example. This example comes from economics. So a store has been selling 200 flat TVs at a week for $350 each. The market survey indicates that if you offer $10 rebate to the buyers, the number of TVs sold will be increased by 20 a week. So find demand function and revenue function, okay? And then how large the rebate should be to offer the maximum revenue, right? So now note that you are asked to optimize what? The revenue. So you want to maximize the revenue. So revenue needs to be maximized and subjected to what? The constraint in the price, right? So in this case, drawing is not applicable. Why? Because now let's try to see the relation between the TV sold and the price per TV. So let X be the price per TV. Sorry, P be the price per TV and X be the unit sold per week. So you'll have what? At 200, you have 350. If you have 220 TV sold, then the price has to be 340 because the rebate is 10, right? So if we do $10 rebate, that means if we reduce $10 from here, for this $10, there'll be increase of 20, right? For $10 rebate, there's an increase of 20 per week. So then the number of units sold would be similarly, if you decrease the price $10 more, it will increase $20. Sorry, the number of units sold will be increased by 20 again. So again, if you reduce $10 more for the price, you will get another, what do you say, another 20 sold. So it will be 260. Okay, so on and so forth. So now these quantities have linear relationship. So we want to find out relation between x and px, right? That's what the demand curve is, right? Quantity sold or relation with the price. So this is a linear relation. So let's exploit that using, so we'll use two of these points to find out the slope. So let's see. So what is the slope? So we can see 340 minus 350 divided by 220 divided minus 200. So this is the slope m. So we get, this is minus 10 by 20, which is minus half. And then you get what? So you, in this case, you get px equals to minus half. So let's write down, let's use this point as x0, y0. So we get what? Px, which is my, like y, is going to be, so px minus 350 equals to minus half, which is the slope, times x minus 20. So bring this on the other side. So you get px equals to minus half x minus 200, and this becomes plus 350. And on simplification, you get 450 minus 0.5x. So this is your demand function. Yeah, there's another way to look at this. Another way to find out the same formula would be, so let x is a number of TV sold, right? Do you agree? So now if x is a number of TV sold, so if you do x minus 200, and if you divide, so if you look at x minus 200, that is the axis of of what? Of the TV sold, right? So the excess of TV sold more than 200 is this guy. And for each of those, each of in the unit of, so this would be divided by, so this is an extra TV sold, and for each, so you are looking at 20 as a block. So this will be the number of, this is the amount of rebate you need to give. Sorry, this is the number of units of rebate you need to give. So if you multiply by 10, this is the amount of rebate you need to give. And then that has to be subtracted from 350. So yeah, so if you simplify this, this is going to be 350 minus, I've calculated the rebate here, which is minus half times x minus 200, which is same thing here, right? So that's another way of computing the, of course, I'm assuming here that x is greater than. Okay. So now we have gotten the price. So now what is the revenue? So revenue is basically price times the quantity sold or the quantity demanded. So we'll have 450 minus 0.5 x, which is the price, times x. This is my revenue. So this is going to be 450 x, so 450 x minus 0.5 x squared. So this is my function, and what is my x? My x belongs to what? 0 to infinity. So you will say, well, x has to be greater than or equal to 200. No, well, I mean, you can sell lesser TV if you basically increase the price, right? Beyond 350, if it can go both ways. So now we want to basically, so question is asking us how large the rebate should be to maximize the revenue. So we want to maximize the revenue. So revenue is basically this function. So take the derivative of it. So we'll follow the guidelines. So find the critical points. So take r prime x, which is 450 minus x. R prime x equals to 0 gives me x equals to 450. R prime x does not exist. There's no such x because for polynomials, the derivative always exists. Now we need to look at the sign diagram. So let's take, say, something between 0 and 450. Let's take 1. If you put 1, 450 minus 1, that is positive. And if you take, say, 460, 450 minus 460, negative. So by first derivative test, this guy will be what? The shape will be like this. So this guy is, we have relative maximum at x equals to 450. Now we need to do the endpoint analysis because the domain is not a closed interval. So remember, if it was interval of the form a infinity, you have to look at x goes to infinity, x goes to a plus of f of x, and x goes to infinity of f of x. So we'll go here in this case, x goes to 0 of, because your a is 0, as x goes to 0 plus of 450x minus 0.5x squared is 0. And as x goes to infinity, this will go to minus infinity because the sign of leading term is negative. So, and it's x squared, so this is a dominant term. So, all right, or you can argue that it's an upside parabola. So the relative maximum is the absolute maximum. So therefore, to achieve maximum revenue, what should be your price? Your price is P of 450, which is 450 minus 0.5 times 450, which is $225. But hold on, the problem is, if you go back to the problem, it's asking how large the rebate should be. So what is the rebate going to be? How much did you discount from 350? So we have this minus this, which is going to be $125. So this is a maximum rebate. Now let's read the following problem. A manufacturer needs to make a cylindrical can which will hold 150, 1500 centimeter cube or 1.5 liters of liquid. Determine the dimensions accurate to one decimal place that will minimize the amount of material needed for the construction. So none of this information will be given to you. You're just given this problem, right? So first of all, what we'll do is we'll draw a cylinder, right? So let's draw a cylinder, right? So and okay, so let's draw the cylinder. All right, so all right. Now this is cylinder. What is the radius of cylinder? The radius of cylinder is, let's say it's R, and the height of cylinder B, H. Okay, so this is from the question. You have to come to the following diagram. Now the question is, so what do we have? We have that the manufacturer needs to make a cylindrical can that will basically hold 1500 centimeter cube of liquid. Determine the dimension accurate to one decimal place that will minimize the amount of material needed for the construction. So what is the material needed for the construction? So what do you really need for constructing this can? You will need the top part, you need the bottom part, which are the squares. So the top is top is a circle, bottom is a circle. They are circle of radius r, two of them, top and bottom. All right, so sorry, my computer got. Okay, so now there's a top part and the bottom part, and they have areas as pi r square because the radius is so 2 pi r square. Now, what is the slant of this? So if you cut side, this side here, and open it up, you will get. So the bottom is the circumference of the circle, which is 2 pi r, and the height is going to be h. So this looks like a rectangle. So the surface area of this guy is going to be 2 pi r h. So the total surface is 2 pi r square plus 2 pi r h. So this is the surface area you want to optimize. All right. Now note that this has two variables in it, right? R and h. So we must exploit the relationship between R and h. Okay, so note the following. We have volume, which is pi r square h, is 1500. So this means that h equals to 1500 by pi r square. So therefore, we can put that back in the equation. So we get surface area is going to be then pi r square, 2 pi r times, instead of h, I'm going to put this. So I get this guy here, and the domain is 0 to infinity. So same things, let's find the critical number for this. So derivative of this with respect to r is going to be 4 pi r, and derivative of this is going to be, what is derivative of 1 by r? Derivative of 1 by r is going to be 1 by r square. So 1 by r square times 3000. And then when you simplify this, you get 4 pi r square, sorry, 4 pi r cube minus 3000 divided by r cube. So s prime equals to 0 would imply the top is 0, which would mean 4 pi r square minus 3000 is 0, which means what? Which means r square equals to 3000 divided by 4 pi, which means r equals to, cancel 4, and so they'll get 750. So this would mean, sorry, there's an error here, it should be r cube. So r cube equals to this, so r equals to cube root of 750 divided by pi. And the second case is s prime r equals to, well, does not exist, and that will not happen because the only time it's zero when r is zero, and that is not part of your domain. Okay, so therefore we have gotten the critical number, which is this point here. Now we need to basically analyze this. So either we use the first derivative test or second derivative test. So the second derivative test will be easier here. So let's take the second derivative test. So what is the second derivative of this guy? So SA double prime of R is going to be, derivative of this is 4 pi. Derivative of that is going to be, what is derivative of 1 by R square? That is going to be plus 2 by R cubed times, and that is always greater than 0 on your domain, right? Yeah, you don't need to, basically this is always greater than 0 and everything else is positive. So you see how second derivative test is better than first derivative test here, but sometimes the second derivative test fails. So in that case, you'll have to go back to the first derivative test. So this is always concave up. That means what we have, since this is always concave up, we'll have that SA has absolute minimum at R equals to this guy, right? Because second derivative greater than 0 means it's local minimum or relative minimum, whatever you want to call it. They are the same thing. And since it's always concave up, this critical point gave you the relative as well as the absolute minimum. So therefore, minimizing the dimension of can. So we want, what does it mean by dimension of can? You need R and you need H. So R, when you plug in your calculator, you get 6.2. And when you put H in this equation, H equals to pi times, instead of R, I'll have what? 6.2 cube, sorry, 6.2 square, and I get 12.4 centimeter. So this is the minimum dimension to get to your minimum dimension so that you can hold 1500 centimeter cube. Okay, so that's it for now. Thank you.